Okay, let's get started. Today is our last lecture on properties of nanostructures, and Wednesday we'll start talking about interactions. So today's topic is the thermal properties of nanostructures, and Aaron Schmidt is going to give the bulk of today's lecture after our recap and intro. The only announcement I have today is, of course, your problem set is due Wednesday, and I'd like you to turn it in at the beginning of lecture, so just bring it up to the front before class starts at 10:40 on Wednesday. Are there any questions about the homework? Okay, then last time we talked about the mechanical properties of nanostructures, and we tried to develop some intuitions as to why and how mechanical properties of small materials can be different than big materials. And we focused on, you could say, that the two most basic and frequently discussed mechanical properties, the stiffness and strength. And mechanical properties of a material are determined by the bonding between the atoms, because the bonds are what hold the atoms together. Many other things like the crystal structure and so on contribute, but we had this basic idea of two atoms being connected by a spring. And as we'll see more next time when we talk about interactions between atoms, we can model this by an interatomic potential. And, for example, estimating or linearizing that potential around the equilibrium point and the equilibrium separation lets us predict the ultimate stiffness and strength of the material. And we find that the stiffness of individual bonds based on this simple model can be close to the real stiffness of materials, because the stiffness at macro scale is dominated by the bond stiffness. However, the ultimate strength, meaning strength determined by actual breakage of the bonds, is realized only in very small volumes, which can be defect-free, because the strength of bulk materials is governed by defects and propagation of dislocations and a lot of more complex mechanisms that relate to how the material is ordered over a longer range. And this let us see that, for example, in very small volumes like carbon nanotubes with very few defects or gold nanowires with very few defects, we could have strengths that approach this idea of a theoretical limit of the Young's modulus divided by 10, or approximately the tensile failure of the material when you've strained the bonds by approximately 10%. And another interesting thing that we can predict and has been verified by a lot of experiments is the fact that you see distributions of strengths in nanostructures. As with large materials, the strength of 10 samples is not always the same, but the spread in the strength of, say, carbon nanotubes is often much broader. And if we could count the defects we have in each nanotube, we could, for example, correlate the strength of that nanotube to the number and placement and type of the defects. And in general, we would have our highest strength, as you could imagine, if we had a defect-free structure, and then the strength would decrease to, you could say, the strength of a bulk material if we had an increasing number of defects to approach the average concentration that we would see in the bulk. And this has been seen for a lot of materials, and is something that you certainly would pay attention to when engineering these materials at the small scale. We also saw another example of, engineering of material structure, and this was more of a top-down approach. And we talked briefly about how there's also a lot of work in controlling the grain size of materials, basically controlling the amount of interfacial area in the material itself, and that is a very facile way to control the strength. And reducing the grain size, in principle, can increase the strength by increasing the amount of area between the grains, and then that reaches a limit, which is something that's currently under study, and the mechanisms by which you can manipulate different properties by engineering the grain size, as well as understand how this reversal occurs, are some things that are under study. And then at the end, we saw that we can actually model nanotubes and other wires and tubes as continuous beams, as continuum beams, when we aren't considering kind of the nonlinear properties such as kinking and buckling and so on. And the only thing we wanted to pay more attention to here was that we want to carefully assign the properties and geometric parameter values. For example, consider the area in the center of the tube as a real hole, as you would in a macroscopic circular beam. And perhaps this is not a surprise, but that says that the real strength of the nanotube actually includes all the area. So if you pack nanotubes together, you got to consider the empty space in the center and also the empty space in between. And before we move on to today's topic, I just wanted to cover a couple more examples. And there are a lot of interesting cases where nature tells us that materials can be engineered on the nanoscale to achieve interesting mechanical properties. And one of the examples that's been studied most widely is what's commonly known as mother of pearl, and this occurs as the coating of a lot of shells of undersea creatures and so on. And the structure, if you slice it apart and look at it in an electron microscope, it kind of looks like a brick wall, where you have platelets of aragonite, which is a type of calcium carbonate, that are stacked in quite a regular fashion, and they're connected by a type of protein, which can be a wide variety of things, but basically you have a very stiff platelet connected by a softer kind of glue layer, if you will. And these are maybe tens of microns wide and maybe hundreds of nanometers thick. And some studies of this material show basically that the role of these glue layers is to isolate flaws in the individual platelets. And as a result of this, the material overall can be both very strong, it can bear a very high load before it fails, and it also can be very tough, meaning it can absorb a lot of energy. And for example, what happens if you have a failure or a crack in one of these little platelets is the fact that you have these proteins that can stretch a lot in between means that that crack is isolated within one of these plates or within a small area around the location of the flaw. So this is a way that the material can sort of have a built-in distributed flaw tolerance and can give a lot of interesting properties. So this is something that you can certainly read about if you're more interested in, and there are many other examples looking at, for example, how other types of undersea creatures organize their skeletons in a hierarchical fashion, as well as things like the multi-layer architecture of snail shells that can be engineered to provide impact resistance while, for example, isolating that impact from the organs that are on the inside. And there's been work we'll see later in the semester to, for example, mimic this structure using self-assembly of nanostructures. For example, one can make platelets of clays or of calcium carbonate by chemical methods or extract them from the earth, and then can lay them down in an alternating process and create this kind of nanoscale brickwork. And another example I wanted to show you is kind of one of my favorites in terms of a real application of how material properties change at the nanoscale, and it actually involves the projectors called the DMDs, or digital mirror displays, that are now widely used for in TVs and in the projectors like this one. And so what you have in a DMD projector is a small MEMS device that contains an array of microfabricated mirrors. And so each mirror represents a pixel, and you have a lamp that's a light source, and sometimes you also have a color wheel in here. And then this array of mirrors, which is not two, but is essentially, say, 1024 by 768, depending on the size of your display. And these mirrors move at very high speed to create the image we see here. So as I'm moving the arrow across the screen, the individual mirrors up there are changing what we see on the screen. And it took about 10 years for Texas Instruments to go through this. They spent a lot of money on it, and I think they've probably now recouped their investment. But the thing that we're interested in here is that it turns out that the support cantilevers, basically the torsional springs that deform as these mirrors are actuated electrostatically, are single crystal beams of nickel. And it's because it turns out that they are single crystal beams of nickel that they're able to deform so much without fatiguing and can handle the extreme number of cycles that you need to have a projector that, for example, plays movies day in and day out. And so you can see another schematic over here where it just shows that the deformation of the mirror, or the tilting of the mirror, can change whether you see light on the screen or whether the light is deflected away to hit this absorber, which is also in the projector. And so at higher magnification, this is an example from a while ago of just one of the architectures, but here you can see more clearly that this multi-layer structure, made using standard microfabrication processes of thin film deposition and etching, has a mirror which is a shiny metal film on the top of a post, and by applying a voltage between the mirror and electrodes down below, the mirror is deflected in the desired directions. And there's a lot of circuitry that sits under here that does the driving at high frequency. And these red beams here are the nickel support beams that deflect a lot. And you can see here, for example, an SEM image where the mirrors are deflected in different directions. And so the hinges that are supporting the mirror here are about 60 nanometers thick and 600 nanometers wide, and they go back and forth by approximately 10 degrees. And if you took a bulk piece of nickel with this aspect ratio and deformed it by this amount in torsion and twisting, you would get plastic deformation of the material after only a few cycles, and it would fail due to fatigue at a relatively small number of cycles. But it turns out that, I don't know if it was by accident or by right-off engineered development, but by controlling the deposition of this nickel film and then subsequent annealing of it, they can guarantee that these beams are individual single crystals, meaning they have no grain boundaries and they have a few or a very small number of defects. And because each of these is a single crystal, then its properties can approach the ideal value we would expect based on the crystal structure. And this lets them realize devices that have an extraordinary fatigue life. So for example, if you imagine that a projector operated for 1,000 hours a year, it's like 3 hours of class in this room for 120 years, so way more than normal. And it always operated in a normal operating range of, say, well, the room temperature is about 25 C, so up into hot weather, they do tests on all these mirrors, and due to fatigue of the hinge, so excluding electronic failures and other things, these things basically don't fail until this number of cycles. Or if you take, for example, that you have 500,000 mirrors in a single device, and this is the characteristics of one hinge, you're pretty much guaranteed not to have failure of the mirrors due to fatigue of the hinge, and so on. So I thought that's just a cool example of how small-scale material properties are taken advantage of in micro devices, and this comes directly from the realization that you can manipulate small volumes to have very highly ordered structures. And that gets us to the topic of today's lecture, and I'll let Aaron take over for the rest of the class.
Okay. You guys hear me? Raise your hand if you can't hear me. All right. Does this work? Let's try this. All right. We'll use both. That's good. Okay. So we're going to talk about thermal transport and thermal properties in materials in general first, and then we'll shrink it down to the nanoscale and see what changes and how it works. What am I doing wrong with this thing? It's lost on the screen. Okay. Okay, we'll do this. All right, so we'll start off with the basic idea of heat transport, what it means to even talk about heat and temperature and those ideas. And we'll go through a little bit about maybe those of you who've had heat transfer before, like Fourier's law and that kind of stuff. And then we'll explore when that starts to break down. Then we'll move on to the individual properties of things like nanowires, thin films, and other things of that nature. And we'll spend some time on thermal interfaces, which becomes especially important as you get really small systems where there's a lot more interfaces for a given volume. And then we'll talk about a couple of special topics, thermoelectrics, so converting heat to electricity and vice versa, and also a little bit on thermal radiation and what happens when you bring things very close together. So here's just some of the reading. There's a little bit in Rogers and Penether. And then there's some extra reading that I'd recommend. This first article is a good overview of some of the kinds of measurements people are doing at small scales and the different techniques they use and some of the theory. And also there's a section from Professor Chen's book in Chapter 3 I'd recommend reading. It's not on here, but where he talks about phonons or vibrations in solids. So let's start off with the basics, heat and temperature and what those mean. And roughly speaking, heat is what we'd say random or thermal energy. So energy without any particular coherence. So it doesn't really make sense to talk about the heat of a ball rolling down a hill. So you need a lot of particles or vibrations moving randomly before you can start to think about it as heat. And strictly speaking, the idea of heat and temperature really only applies to a lot of particles. So from statistical thermodynamics, you need enough that you can begin to use some statistics on them. The way we would define temperature, classically at least, is it would be the measure of the average energy in each degree of freedom. So if you have, say, a molecule, and it can move in 3 dimensions, and it doesn't have any vibration or rotation, then it would be 3/2 times kBt. So for each degree of freedom, you get 1/2 kBt. And even though temperature is a measure of energy, it doesn't have units of energy because the idea of temperature kind of came first in a way. So we had to add this conversion factor called the Boltzmann constant to make them come out equal. But basically, you can think of temperature as energy. And in a small region, even if you don't have a well-defined temperature or a statistical distribution, it still makes sense to talk about the local energy distribution in that area. Okay, so for those of you who've had heat transfer before, this will look pretty familiar, but heat can be transferred, typically we say 3 ways. There's conduction, which is by the motion of vibrations or phonons, by electrons and other particles. Basically anything that can have heat, has a heat capacity, can transfer heat. And then there's convection, which is by the gross motion of atoms and other things, which is really not fundamental, but it's kind of built on top of conduction. So it's conduction plus motion. And then finally there's radiation, so transfer of energy by photons through space. And we're going to spend pretty much the whole lecture today talking about conduction, with just a little bit at the end on radiation. Convection at the nanoscale really doesn't come up quite as often because viscosity and other things tend to limit the amount of motion you have. And also, generally most of the big advances in solid-state electronics and so on focus on conduction. So let's just spend a little bit of time going back to the classical view and diffusion for thermal transport. So here's 2 kind of equivalent pictures of what you might see in a solid. And this would apply to really any kind of solid. You can either think of it as, I'm having no luck today. Okay, well, you can think of it as a bunch of atoms connected by springs, or you can think of it as a bunch of particles kind of floating around in a box. And we'll look at both of these points of view. But the particles can be photons actually, or electrons or phonons, any of these things. And when the particles are bouncing around and when they collide with each other enough, then you can start to think of it as a diffusion process. You fix it? All right. And when that happens, the path of any individual particle will follow what's called a random walk, if you've had any statistical analysis. And you can, from that, produce Fourier's law, which says that the heat flux is proportional to the temperature gradient. And let's just go through a really simple derivation of how that happens, just so you can get a feel for it. So if you have some one-dimensional system with a bunch of atoms bouncing around, these can be atoms like gas molecules, they can be vibrations, electrons, whatever. And we draw some imaginary line through it. And we ask how much energy is flowing across this line. So the answer would be how much energy comes from the left minus how much energy goes to the right. And you have to ask, well, how far to the left of the line do we go, and how far to the right? So if we call the velocity, the mean velocity v, or the x component would be vx, and the average time between collisions, which is sometimes called the relaxation time tau, then all the particles within v times tau to the left will make it over on average, and all the ones that distance to the right will go the other way. And we put this factor of 1/2 because on average half will be going to the left and half will be going to the right on each side. And so when the particles are bouncing around and they're really close, then this distance, v times tau, becomes very small. And in the limit of really small compared to everything else, we can write it as this derivative. And then if we expand the term inside the derivative, so you've got the energy per particle times the number times the velocity, and we take that derivative and we define the energy as the number times the energy per particle, and we take the derivative with respect to temperature, which we call the specific heat, then we can write this expression as this. So we have the heat flux is proportional to the temperature gradient times this factor here. And this we write as the thermal conductivity. So you can express that different ways, but you'll see the thermal conductivity written as any of these different variations. So specific heat times the velocity times either the mean free path, the distance between the particles, or in terms of the time between collisions. And I might express the specific heat in terms of volumetric or versus mass. So that's kind of how the Fourier law would come about from particles bouncing around. But you can see that if the distance between the particles becomes bigger, then this whole definition of the derivative and everything will start to fall apart. If, say, the particle hits the wall on average before it crosses the boundary or things like that. Just to give you a feel for what some typical values are for thermal conductivity, you can see it spans a really huge range. So we've got way up here at the top for bulk materials diamond, which can have a conductivity of around 2,000 watts per meter Kelvin, all the way down for solids down to around 1 or maybe 1/2 for a dense solid is kind of the limit. And the difference being that diamond or other solids where they have highly ordered crystal structure and strong bonds transmits vibrations very well, where disordered materials, the vibrations cannot go very far, and the bonds are much weaker. And then in between here you see metals, like copper, platinum would be in here somewhere, steel. And you'll notice that metals, there's a big range of metals, and the reason is because in metals there's a lot of electrons, and they carry heat as well. So depending on how many free conduction electrons you have, the electrons can contribute a lot to the heat flow. So if we look at this chart here on the right, I've put just some typical materials and the total heat flow, and then how much just comes from the lattice vibration. So you can see that diamond and silicon, which both have a relatively small number of free electrons, it's all due to lattice heat flow. Whereas a material like copper or platinum, they both have also pretty high thermal conductivity, but that's almost all coming from the electrons. And part of the reason why the lattice doesn't contribute that much is because the electrons actually interrupt the flow of vibrations. So they'll scatter off the particles and make it less likely for vibrations to move very far. And there's also a bunch of theory about why these curves behave the way they do. So for example, why does diamond go down at low temperatures and then come up and have this peak and then start coming down again? And you can explain some of that. For example, actually if we go back for a minute, you'll see that our expression for thermal conductivity has the specific heat in it as well as the mean free path. So as you cool the material down, the specific heat begins to go down as the number of available vibrational modes goes down. So you'll see this also later for nanotubes and nanowires. And then as you start to increase, you have more modes available. And then at some point, the shorter mean free path, because they have more vibrational energy, starts to add increased scattering. And that effect begins to counteract the higher heat capacity, and it will come down again. So this will differ for different materials, and amorphous materials will have a whole different curve. But that's kind of the idea. So that's Fourier's law. We want to now look at when does it break. And there's two main cases we're going to think about. One is when the carrier mean free path becomes about the same size as the system we're looking at. So if we have a really thin film and the particles are traveling between one end of the film and the other before they hit another particle, then this won't work. Or also like in a nanowire, for example. And also when we're looking at very fast processes. So like if we consider how long it takes from something to go from one end to the other, times less than that, we definitely won't be able to use Fourier's law because there's no equilibrium established and no diffusion. So these are the things to keep in mind when you're starting to look at a problem. Can I use the diffusion law? And some examples where this would happen. The most common one you'll see is a transistor, like in a semiconductor chip. And here's a typical transistor. You have a source and a drain, and you apply a voltage here, and that allows current to flow from here to here. And as the electrons go from the source to the drain, they have a lot of energy, and when they reach it, they deposit that energy. So below, here's a simulation. This was done at IBM, where they have the electrons flowing from here to here, and then they deposit their heat. And you can see that in this very small region, just a few nanometers, there's all these hot electrons that have all this heat. And within a few nanometers, they have to dissipate all that heat. And in this region, you won't be able to apply the diffusion law because there's not enough space. So you have to use more advanced methods to figure out how that heat is going to be dissipated to the bulk material around it. Other examples you'll see are, say, semiconductor lasers, multiple layers of thin films, where there's a lot of heat generated. And data storage, like this idea from IBM is called the millipede, where you have all these little tips on this thermal phase change material. And you'll bring the tip down, and it will apply a little bit of heat and make a little pocket. And this might be just a few nanometers. So it's like this little bug crawling over, making little spots. So these are all cases where you wouldn't be able to use the diffusion law. Let's see. OK. So before we go into any more detail, I want to do a little bit of background on vibrations in crystals and kind of give you a feeling for what's going on and how we look at this sort of thing. And the details aren't really that important. I just want you to take away the picture that within any structure, there's a whole range of vibrations in different modes and so on. And it's useful to think about which modes are contributing to the heat and which ones get cut off at which size lengths and so on. So this is all from Professor Chen's book, Chapter 3. And you can also find a good description of this in a solid-state physics book. The one by Ashcroft and Merman, I think, is pretty good. So let's start with a one-dimensional chain of atoms, the simplest thing. And we're just going to think of these as balls connected by springs. And we have the spacing between each atom we'll call A, the lattice constant. And these are all vibrating around. And the first thing you can see right away is that there's a minimum wavelength you can have that would have any physical meaning in the system. So if you look at these two wavelengths here, left and right, you'll notice that the dots, which represent atoms, are in exactly the same positions. But the wavelength is different. So this wavelength really has no physical meaning because it's identical to this wavelength. And it turns out that the shortest wavelength you could have would be 1/2 of this wavelength, which is like basically half the atomic spacing, or twice the atomic spacing, rather. And anything shorter than that won't exist in this regular array of atoms. So if we write down really simply the equation of motion for this, you could solve this in any basic dynamics problem. You'd say that the acceleration on some particle, so that u would be the displacement, m is the mass, would be given by the spring constant, and then you could write down the displacement for each particle. And this turns into basically a wave equation. And if we solve it, it has the solution of an exponential, so a complex exponential. And the relationship between the frequency and the wave vector, if you go through, is given by this relation here. So you've got the square root of k over m, which you see is the frequency, and then this term, the sine of ka over 2. So this is the relationship between frequency and wave vector, which we talked about last time we called the dispersion relation. And we said, like, for light, it's a linear relationship. Omega equals just c times k. But we see now in this simple one-dimensional model of springs and balls that we have this more complicated relationship, and it looks like this. So instead of a line, which would be this dashed line here, at the very highest frequencies, it curls over and goes to 0 at the top. And this is plotted, normalized by units of pi over a, which corresponds, like I said, to that maximum frequency you can have in the crystal. So at that maximum frequency, it's flat, and there's no slope. And one thing to think about is that the relationship between omega and k, the derivative of that we can think of as the velocity of that wave, or the phase velocity, we say. So down here, the slope would be the speed of sound in this material, how fast that vibration travels through the chain. So now I'm not going to go through any more math, but we can think about the case where we have two different kinds of atoms. So say a heavy atom and a light atom with m and small m connected by springs. And you can see that for a given wavelength, now there are two possibilities for vibration, two different modes, we'd say. One where all the atoms are moving together, and one where the different mass atoms are moving opposite from each other. And if you went through the same exercise we just did in more detail, and if you want to, it's in the book, you would find that there are two branches, or two solutions for each wavelength, or wave vector. And the first branch we typically call acoustic phonons, or acoustic vibrations, and then the top branch called optical phonons. And they're called optical mainly because they're at higher energy and they can interact with photons, so they have some optical effects. But you can also see that if we consider the slope kind of as the speed of the wave, then the optical phonons have very low speed. The slope is almost flat for most of this. And so for that reason, for heat transport, actually, more of the heat is carried by the acoustic phonons because they have more velocity. So this is all one-dimensional chains, and we can kind of extend this to a real three-dimensional crystal. And this stuff is kind of hard to visualize, but just to take away a little bit of the flavor, we'll consider basically an FCC crystal with two atoms at each basis point. And the crystal we're looking at in particular is indium antimonide, which is a wide bandgap semiconductor used in detectors and things like that. And the way you would solve it is exactly the same, it's just more complicated. You'd consider each atom, and it would have springs and also maybe a bending moment from one or more of its neighbors farther away. And you would set the equations of motion up, and you just let them go, and they'd start vibrating, and you could solve each different mode. And from this crystal, you can see, you've got the different crystal planes, and we can look at vibrations along each of those planes or any combination. So the 1, 0, 0 face, or this one, or this one. And just like we derived, let's go back, this relationship, this dispersion relationship for the 1D, we can get the dispersion relationship for the 3D crystal. And in reciprocal space, like we talked about a couple lectures ago, the reciprocal lattice looks like this for an FCC. So you have here at the center the lowest frequency. They call this the gamma point or the G point. And then going out in different directions, you have these common symmetry points. And this will take a little while to kind of wrap your head around this space and what it means. But you see this all over the place. And the main idea is, in 3 dimensions, in any direction you look, you have all these different directions, and you have a relationship between frequency and wave vector. And the basic rule is for each direction you have, you get 3 branches. And then if you have 2 atoms at each basis point, or each lattice point, then you get 2 additional branches. So 2 times 3 is 6. So in general, along any direction, you'll have 6 different branches. So you can see that here, 1, 2, 3, 4, 5, 6. And then along certain high symmetry lines, some of those branches collapse into the same branch. So we'd call those degenerate branches. So here we only have 4 because these have overlapped. And so when you look at this, you'll see this a lot as kind of it encapsulates a lot of the properties of the vibrations of the crystal. And sometimes it's easy to forget what it means or what's going on. So some important points are that the slope here is the speed of sound in the crystal. So this might be the longitudinal and transverse speed of sound in that direction. And so for a cubic crystal, you'd have speed of sound being different in one direction versus another, or for a FCC or BCC. And you can pick all those elastic constants out from this chart. And it's also nice to think about what this means in terms of actual vibrations inside the crystal. So we've got some movies, if we can play them. So the first is going to be in the 1, 1, 1 direction. So basically along the diagonal of that cube. And we can see that this is, did that work? So this is an acoustic mode, and all the atoms are kind of moving together. So this would be near the center of that zone, where all the atoms are up and diagonally. And now, oops, let's go back. Let's consider a different point. We'll consider the x So at this point in the crystal, in the reciprocal space, this point, the fourth mode. So if we have that point, what does it look like? And we can say it's an optical mode because it's up there, and that probably means that the atoms are moving opposite to each other. And in general, because it's flat, there's going to be no net velocity, no net motion. So if we actually were to look at that, it would look like this. Oops, wrong one, sorry. So you can see that the different atoms moving opposite to each other, and there's really no net motion from that mode. And then you can have more complicated modes at different points within the crystal. Oops. Where it's kind of hard to see what exactly is going on, but these are maybe in a more arbitrary direction. So it's not a real clear distinction what's happening, or if it's acoustic or optical or so on, but you can have any superposition of any of these modes inside a real crystal. And they all contribute a different amount to the heat transport. Okay. Okay. So that's kind of it for vibrations in crystals. It's just a flavor. And for people who have a real crystal, they'll go through and they'll set up these big models and calculate these different modes and figure out what's doing what. And you'll notice that that was all completely classical, just masses on springs vibrating continuously, nothing quantum about it. But it turns out that just like photons, there's a minimum energy for each mode, or amplitude. So it can only come in these small units. And that's given from quantum mechanics by h nu, which is the frequency, and then in integer multiples of 1/2. So 1/2, 3/2, 5/2, so on. So that means that there's a minimum energy carried by each mode, and you'll never get a vibration smaller than that. And just like photons, they obey the Bose-Einstein statistics, so they don't exclude each other from a state, and you can collapse all the modes down into a single state at low temperature. And if you went through and derived it, you could actually find that there's a minimum unit of thermal conductance called the quantum of thermal conductance, given by this relationship here. So it's proportional to the temperature or the energy carried by that mode. Just like in electrical conductance, it's proportional to the charge carried by the electron. And then it's got a bunch of the usual factors, the Boltzmann factor and Planck's constant and so on. So basically, energy eventually comes down, even thermal energy, in discrete units. And people have actually measured this recently. It's a really complicated experiment where you can only see the results at low temperature. But what they've done is they've fabricated this small structure. So you've got pads connecting, and then if you zoom into this middle region, closer and closer, eventually you get to this structure where they've got different connections. And this is, I think, a silicon nitride bridge, and at the minimum point, it's about 300 atoms wide. And that, they figured out, supports only 16 different vibrational modes. And as the heat goes across here, when they get very, very, very cold, then you start to really restrict the available excitations. And what they found is, as they keep reducing the temperature, if you don't assume a minimum thermal conductance, the conductance should depend on the cube of the power. But they found that at this breakpoint temperature, it begins to level off, and you can get no lower reduction in energy. Then it's actually, the interpretation of this graph is a little bit more complicated. If you're interested, you could take a look at the paper about what this really means. But the takeaway point is that they've actually measured this lowest thermal conductance. And in most practical cases, it doesn't matter. I mean, here they're at 100 or 200 millikelvin. And this was a ridiculously complicated experiment, but it does exist. So we've talked about waves. We've talked about how we can also think of them as particles or discrete energy packets. And this is the same slide you guys saw during electron transport, where you've got these different modes. In diffusive, where they're bouncing around, and we can use Fourier's law. And then ballistic, where things go straight from one side to the other, or they'll maybe hit the wall once and then get to the other side. And we're going to see where we cross over from this to this as we shrink our structure size. So we'll take, as an example, silicon, which is a ubiquitous material that's in a lot of applications. And we're going to look at two different charts that came out of a a molecular dynamic simulation. So they set up all these atoms, they put a potential between them, and they just let them go, and then they see what modes come out. And they found that the thermal conductivity, so this on the left is the total thermal conductivity. So for each wavelength you consider, it adds a little bit to the thermal conductivity. And then by the time you contribute all the wavelengths, you get up to 100% of the thermal conductivity. And so they see that, okay, for 1 nanometer, it accounts for about 10% of the thermal conductivity. When the wavelength is 10 nanometers, you get most of the thermal conductivity, about 70%. And by the time you get to 100 nanometers of wavelength for those vibrations, you account for all the thermal conductivity. This is at room temperature. So that means that for most applications, you don't really have to worry about the wavelength. Anything bigger than 10 nanometers, you're not going to see the effect of wave interference. But if you look at the mean free path, so how far that wave or how far that particle goes before it scatters, the picture is a little bit different. So again, on the left, the same thing. How much thermal conductivity is contributed to by each phonon. And this time we're plotting it by the mean free path, or how far it goes before it scatters off another phonon or an electron or a defect or whatever. And you see that now the scale is in microns. So at 1 micron at room temperature, you've only accounted for 60% of the thermal conductivity. And then at 10 microns, even at 10 microns, it's 80%. And you really have to go all the way out to 100 microns before you get to the full thermal conductivity of the material. Now this is a very idealized piece of silicon. There's no defects or no dislocations or anything like that. But even so, it shows that these really long wavelength phonons, or not long wavelength, but long mean free path phonons, can contribute a lot to the heat. So anytime our structure starts to get down to this region, we're going to see some deviations. And here's a couple examples of that. First, what some people did is they took a silicon membrane and they drilled some 2-micron holes in it. And they tried different arrangements, either aligned holes or staggered holes. And then using basic Fourier theory, like if you were to put this in a finite element simulation or just solve the diffusion equation, for each of these cases, you would get these two limits for what the heat flow across that membrane should be. But when they actually measured it, they found that it was significantly lower, by about the fraction that you would expect from phonons with those long mean free paths getting cut off or disrupted by these holes. So even though these are micron scale holes, you start to see some ballistic effects and reduction in thermal conductivity. A more practical case would be, say, thin films, which you see in semiconductor chips. So you've got multiple layers of insulators and crystals and so on. And they also looked at thin wires of silicon. And so what we've got here is the layer thickness of the silicon, or the wire diameter in some cases, going from about 10 nanometers up to, I guess, 500 nanometers. And the thermal conductivity of silicon, bulk silicon, is around 150, just so you have that in mind. And you can see that around 10 nanometers, it's only around 20, the effective thermal conductivity. And then as you start increasing, it begins to approach higher and higher. And even at 100 or 300 or 400 nanometers, it's still 50 or 40% lower than bulk value. And eventually, if you were to take this out to, say, a few microns, this would level off at 150 or so. But these are big reductions and very practical effects that you would see. And when we write thermal conductivity, it's really, you have to keep in mind what they mean. It's kind of an effective thermal conductivity converted back to the language of the diffusion equation. But there are some tricks as how you define thermal conductivity when you are in this ballistic regime that I won't go into now. But if you wanted to just think of it as a thermal conductivity, this is kind of what you would do. And there have been a lot of very clever measurements on measuring things like individual nanowires or carbon nanotubes and fibers and so on. And the basic idea is something like this, where you microfabricate this very complex structure where you have a suspended bridge. So these are really fine insulating material. And then if you zoom in on this part, you see a long platinum wire here and another long platinum wire all coiled up on the other side. And what we know is for platinum, the resistance is proportional to its temperature, the electrical resistance. And we also know that from Joule heating, if you pass a current through, the wire will heat up. It dissipates power as I squared over R. or I squared R or something. So as you send current through here, this wire is going to heat up, and its resistance will change, and it will also dissipate a power that you know. And there's a little bridge connecting this to this, and that's the structure you're going to measure. So this gets hot, heat flows across to this other resistor. And you put just a very small voltage across this to measure the resistance without heating it very much. And you would see two different curves like this. So on the bottom, we're plotting the power, so how much energy we're dumping into this first heater. And you'll see it's got some resistance that's going up as it's getting hotter. And then the other resistor on the other side is also going up. And that's only because heat is flowing through this structure to the other side. And when you design an experiment like this, you have to be very careful that you're not losing heat to other places that would kind of distort your measurements. So these are designed to be very thin and not conduct heat, and everything's done in a vacuum and shielded from radiation and so on. But that's the idea. So you can map out the conductivity of this structure. And so people have done this for all kinds of things, like suspended multi-walled nanotubes or graphite fibers or bundles of tubes. And you can see here, I think the black dots are a multi-walled carbon nanotube, and it peaks out at a thermal conductivity of around 3,000 watts per meter Kelvin, which is higher than diamond that we saw at the beginning, the highest bulk material. And then you notice they all drop down pretty sharply with temperature. And that's from that effect of specific heat. So the number of available modes, as you go lower, it becomes lower, and there's just less vibration to carry the heat. And then at very high temperature, it also starts to curl down again. And that's because now we're getting into the regime where there's more scattering, and that will limit heat. So this will also have a peak, and some of these others would if we carried them out a bit farther. So when you hear people talk about the fantastic electrical or thermal properties of nanotubes and nanowires, this is how we get those kind of measurements. And people have done similar things with even single-walled nanotubes. This is a little bit more complicated measurement. I won't go into the details, but you'll notice that you see the same result, that the thermal conductivity is around 3,000 watts per meter Kelvin. And something interesting you see because of the vibrational modes is that the thermal conductivity actually depends on length, which is something you would never see in a diffusive theory. The conductivity is just a property of the material. But here it's more of a thermal conductance, a property of the structure as a whole. So the longer wire actually will have a higher thermal conductivity, which is interesting and purely a size effect. And the last thing is we talked about ballistic transport and what that means. So if we do this measurement with very short wires, we would expect that as we make them short enough, the heat particle, say a phonon, might be able to go from here to here without touching the wall at all. And in that case, the thermal conductivity wouldn't depend on the length of that wire. So people have taken a setup like this, and they've measured wires, and they've just kept increasing the length of the wire. And when they plot it, so this is plotted in terms of inverse length for whatever reason. And you'll see that, so down here is the long wires, and then out here, this is, these wires are, I don't know, maybe 100 nanometers long. So we go from several microns down to 100 nanometers. And you see that the power per area is going up, up, and then it just levels off. So as you shorten the wire, it stays constant. And that's because you've reached this ballistic limit where the energy is going straight across the wire. So if we were to design something like a single nanowall, heat conductor or a transistor or whatever, you would see that it wouldn't depend on this, and you would take that into account. And you also see this in things like polymers or molecular chains. So there's this idea that if you were to take a polymer, which is normally all disordered, and stretch it out until all the chains were aligned, you could, in theory, create a really good thermal conductor. Just like if you have an aligned forest of carbon nanotubes, it should be a good conductor. And to measure that, we've done some very fancy optical experiments. The idea is that you have, say, a layer of gold, and then you, on top of that, put this, they call it a self-assembled monolayer. So a bunch of these molecules with a certain end, and then a long tail, and then another molecule. And you shine a heat pulse, an ultra-short heat pulse, like a few femtoseconds, onto this gold film. And that heat pulse travels through the gold and couples to the bottom of this molecule. And then it travels along the molecule, and when it reaches the end, it causes some shift in the frequency spectrum. So there's this kind of emission effect you can detect. And so they did this for different length chains. So they assembled these monolayers of different lengths, and then they measured the time it took to go from here to here for that heat pulse. And they found that as you increase the chain length, basically that time between here and here is linear. So you're measuring the speed of heat propagation along that molecule, and it's like about 1 meter a second, they found. So this is ballistic transport. And the other interesting thing they found is as you decrease the chain length, eventually you get no delay time, around 4 or 5 atoms. And that means that this interface really isn't gold and then 1 or 2 carbon atoms, but it's kind of a mix of about 5 atoms. And that vibration more or less instantly talks to the first 5 atoms, and then that propagates down the chain. So this is a very clever experiment, and it kind of gives an idea of what might be possible if we were to stretch out polymer atoms as well. Okay, so the next big topic I want to talk about is thermal boundary conductance. So as you get to the nanoscale, you have a lot of interfaces close together. And we should talk about how we deal with those interfaces and even what it means. So from regular heat transfer, if you've had that, you'll see that they use something called Newton's law of cooling, or they've called it other names. But basically, the heat flux is proportional to some constant, which we'll call G, times the temperature difference across that interface. So there's a temperature discontinuity, or a jump. And in the macroscopic sense, when you take two things and push them together, like a heat sink on a CPU chip, or a radiator on your car, or whatever, there's some gaps, some large-scale spaces. And you might want to fill those gaps with a thermal grease or something, but most of the resistance is caused by these gaps. But when you go down to nanoscale, if you're making chips, for example, you can create atomically perfect interfaces, or almost so. So when you deposit a metal on a semiconductor or a glass, you get an interface that's really like this. And even in this case, you still get this kind of effect, this discontinuity in temperature as you go across the interface. And this is caused by a more fundamental mechanism, which is the fact that the vibrations as they approach these different atoms get either reflected or transmitted. So you can think of it just like light waves going from one material to the other. And the way they reflect or transmit at this interface is complicated, because as you saw, there's all these different vibrations in different modes, and different ones will get through. So there's been a lot of effort to kind of understand this process. And there's some simple models that people use that kind of predict the right trends, but don't really give you a good quantitative picture. I'll just go through one of the most basic ones now. So we talked about how phonons can either reflect or transmit at the interface. And the model you'll see most commonly used at room temperature is called the diffuse mismatch model. And that model assumes that whenever a phonon gets to the interface, basically it forgets where it came from, and it scatters randomly into any direction. And the rationale behind that is that even at, say, 1 atom roughness, a room temperature phonon is pretty likely to scatter. So this idea of a phonon forgetting where it came from is actually pretty good. And if we look at the formula for that, don't worry too much about what it means, but the idea is you integrate over all the different modes in the crystal, so all the different vibrations, this function, which is the transmissivity, so what's the probability that the phonon will get across the interface, the energy per phonon, so h bar omega, then the speed, and then the density of states, and this distribution function. So all stuff we've talked about before. This is the number of phonons we're going to find in a state, how much energy they carry, how fast they're moving, and then we differentiate with respect to temperature. So this is kind of the idea of how people model this kind of thing. And there's complications, which modes and which polarizations and a lot of stuff, and it doesn't work well anyway, so I wouldn't worry about it, but it gives you the flavor. Some typical values that you might see. You expect that as the two materials are really different, say something very soft and very hard, like at the bottom here we have lead and diamond. So lead is really heavy and really soft, diamond is light and extremely stiff. The thermal conductance is extremely low, around, I guess, 20 megawatts per meter squared Kelvin. And actually, that's really high compared to like pressing two solids together. It's orders of magnitude higher. But as far as perfect solid-solid contact, that's about as low as you can get. And then as your materials become more similar, like aluminum and aluminum oxide, or they've even found higher ones, it becomes higher and higher. And eventually, this solid line is that model that we just talked about, the diffuse mismatch model. So, the model is pretty poor in this case, but you see that it's kind of an upper bound, and it catches the right trend. So let's talk about a couple of examples where this might be important. One is interfaces between carbon and metals. So we've talked a lot about nanotubes in this class. You also see things like graphene or graphene-based electronics. And the idea is anytime you have either a nanotube or a piece of graphene in contact with a metal, there's going to be this effect. And pretty much you always have it in contact with a metal because you need to make electrical contact or thermal contact to get your signal in and out. So the question is how much heat gets into the metal from the nanotube or vice versa. And you can imagine connecting it along the side, so if this is the c-axis, or along this plane. So there have been measurements made for different metals on graphite, like highly ordered graphite that's very similar to the wall of a multi-walled nanotube. And you can see that they all follow this kind of trend predicted by the model, and that for the softest metals, like gold versus graphite, it's considerably lower than stiffer metals, like aluminum on graphite. And down here, the highest one is titanium on graphite. And some of the other effects that go into this are how well the metal actually wets the carbon and how well the interface mixes and so on. But this is the general idea. So if you were building a device, you might want to add a layer of titanium before you put on your other metal to make better contact with your carbon nanotube or your piece of graphite. Another example that we'll come back to in a little bit is this idea of superlattices. A lot of research was done on this topic about 10 years ago. And it's produced by growing alternating layers of two different materials that are well matched to each other. So they have similar lattice constants. In this case, it's silicon and germanium. And these layers are just a few nanometers thick. And so this will go on for hundreds of layers. And you get this material that's basically nothing but interfaces, essentially. And you can imagine this is going to have a very different vibrational spectrum. And if heat is reflected at each interface, it's going to have very low thermal conductivity that will be different from the bulk. And there's ways to model this where you assume that when the phonon or the vibration gets to here, do we assume it reflects specularly, or does it reflect diffusely, or do the waves interfere? And there's a lot of details, but there was a lot of excitement about this kind of material for tailoring thermal properties. And here's just a few measurements from two different kinds of superlattices. One is silicon germanium, and the other is gallium arsenide and aluminum arsenide. And people have tried to use this for things like semiconductor lasers, where you've got lots of layers, and also for thermoelectric materials, which I'll talk about in a little bit. But you can see that there's this strong dependence. So each of these different symbols is a different period. This is, I think, 65 angstroms. And then, I think these are angstroms. So 65 atoms, more or less, 50 atoms, 30 atoms, and so on. And you can see that the number of atoms in each period affects the thermal conductivity across the superlattice. And you see a similar trend for the gallium arsenide, aluminum arsenide. Although you'll notice that the temperature dependence is different because of the different nature of the materials. But the main point here is just that by tailoring these layers in the materials, you can strongly affect the thermal conductivity. So let's talk about an example where this is important, and that would be thermoelectric materials, thermoelectricity. And you may have seen this in terms of like a Peltier cooler for a chip or a solid-state cooler, or for a power generator. So for example, on like deep space probes, they'll have a radioactive isotope, and then they'll wrap these solid-state energy converters around them, and that will power it as it goes deep into space where there's no sun. And you can run this either backwards or forwards. The effect is basically the same. What happens is you have metal, and let's say we're running it in cooling mode, for example. You have a metal, and you apply a voltage, and then the electrons approach this semiconducting material, and when they get there, there's a gap in energies from the level in the metal, which is like the conduction band, to jump up into the conduction band of the semiconductor. And because there's this gap, only the most energetic electrons can make that jump. So they heat up. And as they come across, they get to the metal, and those hot electrons come back down, depositing their heat on the other side. I guess I'm talking about this case. And basically what people will do is they'll put two of these materials in parallel. And one will be, they call it N-type, which will have an excess of electrons, and the other will be called P-type. So there'll be a lack of electrons, and the carriers are called holes, which are basically, you can think of them like positive electrons. And the idea is that these have opposite thermoelectric effects. So as the current goes from here to here, in this case, this end gets cold, and in this case, this end also gets cold, even though the current is running in opposite directions. So each of these little couples, this pair, can be used to generate heat or to get electricity. So if you have heat and cold, it runs in reverse. And in a practical device, you might put together a whole bunch of these. So each of these little structures is one of these little legs. And each one generates a tiny amount of electricity, but if you put a whole bunch in parallel, then you can generate a sizable amount of electricity or a sizable amount of cooling. The problem is it's not really very efficient. So in niche applications, like in a satellite, or if you just want to cool down a chip locally without lots of messy water and so on, it will work. But if you want to be competitive with things like refrigerators or engines or so on, it needs to become a lot more efficient. And the way we judge the efficiency is something called the figure of merit. And that depends on a few different things. The first is this thing called the Seebeck coefficient, which is basically the amount of voltage you'll get for a certain temperature. So it comes from the fact that the energy carriers actually also carry heat. So if you have a voltage and you have a current, you're also transporting heat. And that goes into the Seebeck coefficient. The other factor is the electrical conductivity. So you want the material to be able to transport electrons very well. And the thermal conductivity is on the bottom. So you don't want heat to flow backwards through your structure, or that will degrade the performance of your device. So you've got these competing effects. And the problem is that most materials that are good electrical conductors are also good thermal conductors. So it's really hard to get something that conducts electricity very well and that conducts heat very poorly. And that's where a lot of the work has been done to try to improve thermoelectrics recently. Yeah, so this factor needs to be around 2 to 3 to really be competitive with, say, a refrigerator that you would buy off the shelf. And right now it's been stuck at around 1, although that's been improving. And like I said, the ideal material, if you could engineer it, would be something like, for electrons, it would behave as a crystal with high conductivity, whereas for the vibrations or phonons, it would be disordered like a glass and really restrict heat flow. And if we look at progress in this figure of merit, this quantity that judges how effective the device is, we see an interesting thing. So it was first discovered, I don't know, in the 30s or 40s, and there was some progress with these kind of strange alloys like bismuth telluride and lead telluride. And then things pretty much got stuck for about 50 or 60 years. And then just very recently, in the 90s, people started playing with things like superlattices or quantum dot superlattices. And now, even more recently, kind of nanostructured random materials, like where you grind up like silicon germanium or bismuth and telluride into nano-sized particles. So you create lots of interfaces. And suddenly we see this big jump in the figure of merit in a very short time. And this is all due to reducing the thermal conductivity while keeping the other properties the same. The problem is that these are still really expensive to make. So in theory, we can make ZT of 2 or 2.5, but it would cost way too much to make a practical device. So now a lot of work is being done to kind of bring this kind of idea into something we could manufacture at a large scale more cheaply. And there's been some interesting experiments. This is done by Professor Reddy, who's in the mechanical engineering department here, where you can even show the thermoelectric properties of single molecules. So as energy goes across, there's a temperature difference. And this is a very delicate experiment where basically this collection of gold atoms is the tip of an atomic force microscope, which I think you've talked about. So it's just like a record player scanning along the surface. And the tip is cold, and then there's a gold substrate, so a film of gold that's been heated up by a certain amount, say 20 degrees. And when you bring the tip in contact with the gold, if there's no molecule there, then there's going to be no change in voltage due to the temperature difference. So this kind of reddish line here, oh, it works now. All right, this kind of reddish line here is when he brings the tip into contact when there's no molecule there. So even though there's a temperature difference, when you touch these together, there's no voltage jump, basically no thermoelectric effect. But then he puts this single molecule on the tip, and when he touches it, because there's a temperature difference, there's a voltage jump. And that's due to the Seebeck effect in this single molecule. And then what he does is he'll change the temperature of the substrate different amounts. And he'll see that the size of that voltage jump changes. So here, at 10 degrees K, you get this small jump in voltage. At 20, it's bigger, and at 30, it's bigger still. So this is measuring the change in voltage from that single molecule under the thermoelectric effect. Okay, so let's switch topics a little bit. This is a more general technique for measuring thermal transport at the nanoscale, kind of along the same idea, where you have a scanning tip. And there's a general class of tools called scanning thermal microscopes that work on similar principles, where the idea is that you have a tiny thermocouple at the end of your AFM tip, and you have a heater. So you're sending heat, and then you're measuring the temperature. And you maintain a fixed distance above your substrate, or you're in contact with your substrate. And then you can measure the temperature. And since you know how much heat you're dumping in, you can figure out the conductivity of the substrate, or at least the relative thermal conductivity. So it provides you a way to map out thermally conductive regions. So you can see here the pitch here is extremely fine. I think the resolution is less than 100 nanometers now. At the time this was written, it was around 100. So we could probe. You can imagine, for example, if you had a tiny transistor in an Intel chip, you could actually produce a thermal map and see where the hot spots are and how that heat is distributed on the order of the transistor size itself. Okay, and now the last thing I want to mention is thermal radiation. And this is a totally different topic, and I think we'll come back to some of this stuff later when we talk about surface plasmons and optical properties. But it's related in the fact that it's a thermal energy process. So for those of you who've had thermal radiation before and heat transfer, you might remember that typically there's a relationship for a black body radiating energy. And it goes as this constant, the Boltzmann constant times temperature to the 4th power. And in theory, when you bring two objects very close together, you can exceed that limit due to nanoscale effects. The idea is that, in general, for photons, they're propagating electromagnetic waves. And if you have a hot material where all the atoms are jiggling thermally, there are little electrons, and they're emitting these waves, and they're propagating. But in certain materials, you have these trapped modes on the surface. So the electromagnetic field is interacting, and all the electrons might be oscillating inside the material at the surface, or they might be interacting with phonons at the surface. So these surface waves would be called plasmons or polaritons or other names. And the idea is that there's propagating waves, and then these surface waves are kind of bound, and they decay exponentially away from the surface. So you can think of it like this, where you have, say, two plates, for example, and if they're of the right material, you'll have both these propagating waves coming out and also these bound surface modes. And the surface modes will decay over a distance of a few hundred nanometers. So normally, when the plates are far apart, you get the black body radiation law. But if you were to bring them very close together without touching, say within the distance where these decaying waves could interact, you could get additional heat exchange. And there's been talk of how we could exploit this, for example, bringing two plates very close together to make a really powerful generator based on, say, photovoltaic energy. So when you have a localized heat source, they call it a thermophotovoltaic generator. And there's been talk of bringing very close plates and making very efficient thermophotovoltaic generators using this principle. And it depends a lot on what materials you use here and picking the right ones that support these special surface modes. But in theory, it's possible. And for a while, people tried to do this experiment, and it turned out to be very difficult to maintain this tiny spacing without touching, because if they touch, then the thermal conduction will overwhelm the radiation and make it difficult to see the effect. And then just recently, someone succeeded using a slightly different idea. They took a sphere and they put it on an AFM tip and they brought it very close to a flat surface. And they solved for the heat transfer. And what they found is this solid black line here. So this is the heat, this is the heat transfer on this axis. And this black line represents the black body radiation limit. And as they bring the plates closer together, around 500 nanometers or so, you start to see that the heat transfer goes way up. In the end, it's many orders of magnitude higher than what you'd get from black body radiation. So this is an example of how, in theory, when you push these limits, you can beat these laws, and sometimes by a lot. Now, like I said, to do this in a practical way with plates spaced close together in a real device is still a big challenge, but the opportunity is there. So I guess that kind of wraps up the discussion we've had on energy carriers. I know you've seen some stuff from John and myself. We've talked about atoms and photons, phonons, electrons. And hopefully you've seen that there's a lot of similarities in the way we look at these things. There's this whole idea of treating them like waves or particles and the limits of those regimes. So when your structure becomes the size of the wavelength, if it's electrons, for example, you get discrete electronic states. For phonons, you get vibrational states. And then this idea in the particle picture of scattering and traveling from one spot to another. And again, when the particle can go across your structure, then you have to worry about things like ballistic effects. And if you look in, say, Professor Chen's book or other books, they'll give you these kind of handy charts about, the typical velocities of these particles, and there are other charts where they'll show the typical mean free paths in different materials or different scattering times. So you can get a feel for, if I'm looking at this film of this material at this temperature, when will I have to worry about these ballistic effects? And when will it matter? And we really didn't talk at all about how you model them. It's pretty complicated, and there's a few different techniques and some whole classes here at UMich about modeling things using ballistic transport and that kind of stuff. But at least you'll be aware of when you'll start to worry about it. So I guess that's it. Any questions? Okay.